Okay, I think we can start. Good morning, everybody. And today we have the exercise session by Simone Rodini, which is related to the course given by Barbara Pasquini in the afternoon sessions on the multidimensional structure of the proton. So Simone is a postdoc in Regensburg. He got his PhD in Pavia, and now we want to listen to his lecture. Please, Simone.
Thank you, Sergio. So you should see my screen. And okay, so first of all, I encourage you to ask questions, not just on the topic of these exercises, whether they are questions about the specific exercises that we will do together or something related to what I put on the document or whatever you want to call it, but also questions on the content of the lectures of Barbara Pasquini. So she thinks that you are shy because she's professor and you do not want to embarrass yourself with questions that could be stupid or could be simple, or you simply didn't have enough time to think about questions to ask her. So if you have any, please ask me, and I will try my best to give an answer that makes sense. So since today we have 2 hours, I think I will start from the end, and we will do the dipole calculation because it is simple but quite lengthy. Well, not really, but it will take a little bit of time. And tomorrow we will cover the remaining topics, which are Fourier transforms, GPDs, impact parameter distributions, and so on. If I will have time at the end, if you didn't see it in other exercises, maybe we will talk a little bit about rapidity divergences, but only if I have time and only if you do not have a question. So it is really the last priority. So I will start with type work. If at any point you think something is not clear, stop me, ask me, and I will try to either correct myself if I said something stupid or give you an answer for why I did what I did. So the Lagrangian of the model. So the idea is that, okay, in principle, you have something that looks like this that you want to compute, which is the TMD distribution with, for now, let me put a generic gamma matrices in between. So there also should be 1/2 for the kind of definition that you use, Q of Z, and then proton state P, and everything here is evaluated Z plus equal to 0. So you have transverse separation between quark and anti-quark, or Q and Q bar fields, and space-like separation on the light cone, since Z minus is the space-like component of light front coordinates, and Z plus equal to 0. So basically it is an equal time correlator on the light front. So here already I'm neglecting Wilson lines because I have in mind to use Dyck-Work model, and this already tells you that, okay, Dyck-Work model is maybe not the best thing to do if you want to have a real picture of the protons, since, as Professor Dill discussed, Wilson lines are linked to, in the TMD case, are linked to physical effects, like the series, the change of sign of serial distributions. So the idea is that we want to construct a model for how this proton field that lives in the states interacts with our quarks. So the simplest thing to do is assuming a vertex between what you call proton field. So you just say, okay, the proton is a degree of freedom in my theory, or it's not QCD, and with, of course, you want the quark, and you want, okay, something else, because you cannot have just 2 particles that enter to a vertex of interaction. So you more or less guess a Lagrangian that looks like a free part, which I will not write, but it contains the free part for the proton, the quark, and the Dyck-Work field. And you put an interaction that looks like a coupling, which, okay, you have to have. This is this capital psi, and I hope I will write it well enough, is the proton field. Then you have the interaction with the quark field, and this incidentally saturates the Dirac structure of the two fields, since both of them are spin-1/2 particles, so to saturate Dirac indexes. And then you put the simplest dipole possible, which is just a scalar particle. And then you take the complex conjugate of this to a nice construction. So this is your Lagrange. So once you have the Lagrangian, the first thing that you want to do is perturbation theory, because otherwise we face the same problem that we have in QCD, that we cannot compute things non-perturbatively. And once you have perturbation theory, one method to actually build perturbation series of the operator that you are interested in this case is matrix element, is using the functional integration. So to do that, you have to realize that, okay, since we are working at z plus equal to 0, this correlator that we are using is actually equal time correlator, so we can basically trade this with the order products. So we can usually we can use the functional integration method that you see in quantum theory classes, so more or less done. But I would like you to appreciate how this actually works, so how you get this z plus equal to 0. So let me write the usual TMD correlator in a slightly different fashion. So it is the integral over the minus component of the momentum, the external momentum, and then you have the 4-dimensional Fourier transform of, in this case, the exponential I pz, or incidentally, you will see a convention with plus and minuses here, z, and the z is reversed in the correlator. That's convention. Then you have your proton state, and you have q. Let me write psi bar 0, gamma psi z. Okay, it should be clear that this is exactly the same as this gives you basically 2 pi delta of z plus, right? So it is exactly the same as the TMT correlator, but we will keep the integration over p minus explicitly, and we will use it at the end, and I will show you what actually means. And you usually see diagrams in which you have the cut between the TMD operator. So here enters your proton, you have your quark or anti-quark, whatever, and you put this cut, and you know some Feynman rules for these cuts, but I would like you to appreciate how actually in computation this arrives. So once you have this matrix element, you just promote it to functional integration. So so first of all, you write. I will not write literally everything, otherwise we will stay here for a month. But you get the integral over p minus, the integral over the 4z 2 pi 4th, the exponential. Then the proton state is nothing else than the creator of a proton field with momentum p on the vacuum. Just since the proton is a degree of freedom in your theory, you just have the creation of the proton over the vacuum. So you can write this as the vacuum matrix element of psi of p, and then you have your and then you have psi bar of 0, gamma psi of z, and then you insert here, you insert your interaction Lagrangian. So you expand and you write the functional integral, you expand your Lagrangian. So basically you need, in the model, you need 2 vertices, because you have to to saturate both psi bar of 0 and psi of z. So you get Ig squared over 2, which is the 2 is the symmetry factor because you have two integrals in the expansion of the exponential, and Ig squared is just the coupling. And then you have the integral over, let's use the same convention. In this case, since we are not doing one loop calculations, so this is basically just tree level, we can forget about d-dimensional, 4-dimensional, it's just 4 dimensions, and we're fine. So y and w are the two coordinates of the interactions that we put in, and then we need one that looks like the proton bar psi of y, phi of y, and another that looks like psi, which is the quark one, w, psi of w, phi of w. And then, so everything here is inserted. And then you have your psi dagger of p over the value. They should be rather standard. And now you just have to saturate. So basically, you decontract the fields, which needs to be. And you notice that you can write on the light front a decomposition for, let's say, C of W as dq. This is the Lorentz invariant measure. So there should be an exercise. This is standard. It just changed with respect to instant formula. There is nothing there. Then you have the positive frequency wave. And then you have your C of Q, U of Q, where U of Q is the light front spinor. And in this notation, this is the structure, the annihilation operator of the proton field with momentum Q. And then you have, even if we do not need it, we have the anti-proton, let's call it capital Phi. This is the anti-proton, but we do not need it, but in principle in your theory. So, and basically you can do the same for C bar of Y. Then you have your integral over dq, EQW, psi dagger of Q, C bar of Q, plus the anti-proton. So once you have this, another relation that you need to compute it. So it is basically useful to write down your relations first, and then you look at what you need to compute and just apply these relations over and over again. So psi W, so W is position.
Hello.
Yep.
Yeah. Just a short question. In the W, in the psi W, psi Y, Y in the exponential there are W.
Yeah.
Okay. Okay. I threw it was other things, but okay.
Yeah. Thank you. Okay. This is one stupid stuff that I can do. So in if we go back, okay, you see that you end up having this psi dagger of P, which is momentum P, and psi of W, right? So you need to know what actually this combination means, because you do not want in your operator, you do not see the proton. The proton is just a state, and you have to annihilate it. So you have to actually say something about what this psi W, psi dagger of P means, or is. So you have your psi dagger of P that acts on the vacuum. So this, okay, we replace just the what we said that is the momentum representation of CW. So we just end up with the integral over the Q, E minus QW, and then you have the anti-commutator between C of Q, C dagger of P, U of Q, that's on the vacuum. So why you get just this? Because if you plug the antiproton, you are computing something else. So the antiproton stuff is not relevant for us. And once you compute something that looks like C of Q over the vacuum, so this tries to annihilate a proton over the vacuum. So this gives you exactly 0. So you just end up with something that looks like this. And one of the exercises, okay, once you know what this commutator is on the light front, and it's just 2 plus, or just better, 2p plus delta of q plus minus p plus delta 2-dimensional of qt minus pt, and then 2 by q. This just gives you u of q, the vacuum state, and then you end up with the minus e pw with a theta of p plus, but okay, this forget about it, because in light from quantity, so the proton state, this is physical proton, so it has to be on shell. And you can prove that massive state, which is on shell, is forced to have positive p plus. Just you can get it. P mu, this is instant form quantization in the rest frame. This is 0, 0, 0. So this is time, and this is space. And you can see that, okay, in light from coordinates, so this is plus, this is m over square root of 2, this is minus, which is m over square root of 2, and then you have delta t, right? This is translation between instant form parameterization and light form parameterization. And as you see with the lectures of Deal, you can basically, the momentum is boosted, or any vector is boosted if you boost along the light front, which is what we are doing. This plus and minus momenta basically just gets something that looks like E of omega times whatever it is there. Since the exponential is positive, always, you just have positive plus momentum if the particle is on shell. Off-shell particles can do whatever. So, okay, so we have the theta of p plus is just 1, since p plus is always positive and non-zero. So we do not have problems. So basically, the two p's that are important for us are this u of q and this exponential. Why? Because okay, the vacuum state will be absorbed by the normalization at the end. We just don't care about it. And the theta I just explained. So if you go back and you look at this this correlator, you can I think see immediately that since these two highlighted these two highlighted proton states basically set up your chain of how you should see the structure, the direct structure of this object. So you contract this psi bar with this psi, and then you go through the chain and you contract this psi with this psi bar, and then you have your proton state that is saturated with this psi bar of y. And of course, you have nothing else to do than contracting your dipole fields, this scalar fields. Okay, so once you do that, and you remember that you can write psi of z, psi bar of y. This is just random letters, so if I use different conventions, I'm sorry, but this is the Feynman propagator for the for the Dirac field. So this is just depends only on the difference, you know that. And you have a representation for this into momentum space that looks like 2 pi to the 4th E minus I Z minus Y Q. And then you have Q slash plus M over Q square minus M square plus IX. So this is should be rather standard, just for reference. Well, the scalar propagator is basically the same. This is nothing else. Well, okay, I just use the different letters for the mass of the scalar field compared to the Dirac field. Basically, it is the same. This is standard stuff. So your correlator becomes minus G squared. It comes from the minus comes from the I squared over 2, which is the symmetry factor. Then you have the integral over P minus, the integral over the 4Z 2 4 pi E PZ. And then you have your no, I put some different. You have your vacuum U bar P. Then as an intermediate step, let's plug E S of Y that comes from this dotted field, right? See, you can see it translates from Y to 0, so it's Y. Then you have your gamma matrices that defines what you are computing as in the operator. Then you have your propagator from the position Z, which is the external position of the field minus W. And then you have your U of P vacuum, and then you have exponential of minus E P W plus E P Y, which comes from these the stuff that I just told you about the field. So few remarks. Here I'm not writing the integral over Y over W, so it's I will keep these integrals just for your convenience, but okay, remember that these are integrated over Y and W. And it is implicitly, once you use functional interval formalisms, it is usually implied that you are dividing by the vacuum normalization, which looks like just you can write it as the vacuum normalization, which is understood to be computed at the same perturbative order as you are doing your calculation. So basically what it means that the contraction that I did are the ones that exclude vacuum bubbles of any sort. Right? So I just computed one set of contractions that guarantees you the flow from the vacuum to the vacuum with a connected graph. But in principle, you can do you can create vacuum bubbles when you do perturbative calculations. But those are part of the vacuum normalization, and this is normalized away in standard computation. So in principle, you have vacuum bubbles, but you normalize it away. And if you really want to see the cancellation, you can just compute everything for the vacuum and see there is no point here. So the Feynman diagram that correspond to this, and forget about the integral over P minus for a moment, you just annihilate your quark. So these x's are the external fields, where external means the fields that you are putting into your matrix element. So this is not a scattering matrices, because okay, you're not putting the identity between the states, the initial and final states. You're putting some operators. So these operators annihilates from the corresponding operators of perturbative series. Then you have your proton states that act as these external spinors that saturate the Dirac structure. And in between, you have your scalar propagator, which I, of course, forgot to write. Here you have also your scalar propagator from Y to W. So this was, I did forget the scalar propagator. So basically, you are computing this Feynman graph in which, I repeat, this axis means that you are absorbing these fields into the external operator, which you can do. And this is non-local, so you have actually two saturation points instead of just one. If you compute a local operators, this would be in the same spot instead here separate. So what we can do now is plug the momentum representation for these propagators and just have a beautiful chain of stuff. So you can do that by, okay, this is I. So this minus saturates with two of these i's and one I is left. So you get I g squared over 2. Then you have your integral over p minus, the integral over the 4z over 2 4 pi e pz. Then you can, I think you can see now, you can just remove the vacuum. Since, okay, this is no longer operators, this is just propagators, it's fully contracted, so you can just remove the vacuum normalization and remove the vacuum states. So, and now you have, let me give names. So this S of Y will get momentum Q1. This second S of Z minus W will get momentum Q2. And the scalar propagator will get momentum Q3. This is just nomenclature. You can do whatever you want. Just give names. So you have the integral over the Q1, 2, and 3 is this 2 pi 1 2 pi to the 12th for the momentum transformation. Integral over Y and W. This is 4 dimensionals. Now I will write everything just for your convenience. And then you have these two exponential from the proton state. So it is minus IPW plus IPY. Then you have the exponentials for the propagators. So the first one is minus IQ1Y. And these are all 4-dimensional products. Then you have the second one. So it is minus IQ2 of Z minus W. And then minus IQ3 of Y minus W. These are all the exponentials that you have. And then you have your Dirac structure, which looks like U bar of P, Q1 slash plus M over Q1 square minus M square plus I epsilon, gamma, Q2 slash plus M, Q2 square minus M square plus I epsilon, U of P. And then you have the scalar propagator, which is U3 squared minus MX squared plus. Okay. So this basically, these are just a bunch of integrals. Most of them will go away with these exponential functions. And then you have your Dirac structure. This is, let me say, the more or less the most important part of this calculation. So you have your beautiful Dirac structure with which you can do basically everything you do. So how do we continue? Now let's observe that the integral over Y, so let's put double underline to isolate the piece that we need. So this is IPY minus Q1Y, and then you have this piece here that contains Q3. So as the integral over Y goes, you get 2 pi 4th the delta of P minus Q1 minus Q3. Then the integral over W, it gives you Q2, but okay, remember there is a minus sign, here Q3 with a minus sign, and here P with a minus sign again. So you get 2/4, the delta of minus P plus Q2 plus Q3. And then finally, you get your integral over Z. So it gives you this small p. And the only other piece that depends on Z is this key. So incidentally, you see that we separated all the exponentials, so they all go away. We separated the 3 position space integrals, so they all go away. And this leaves you with extra 2/4, the delta of Q2 minus small p. So now this is just kind of stupid algebra. So this is Q2 equals small p. Then you have Q3, that is, if you look from here, this is just p minus Q2. This capital P minus Q2, which is nothing else than P minus small p. And then Q1 from the first one, you get as P minus Q3. This is just small p. So there is really nothing there. So the factors 2π is cancelled with this 2π12. This 2π12 is cancelled from those factors of pi. The deltas are removed by integrating over Q1, Q3, and Q2. So all these integrals are also removed from the deltas. So you are left basically with prefactor integral over p minus of whatever here computed with the correct q's. So you're left with ig squared half u bar of p, the integral over p minus u bar of p, p slash plus m p squared minus m squared plus I epsilon gamma p slash plus m over p squared minus m squared plus I epsilon. And then, sorry, u of p, and then 1 over p minus p squared minus mx squared plus epsilon. So you see that I did nothing else than replacing the small q's with their corresponding counterpart. So now the problem is basically over. So we just basically finish it. But a couple of stuff that needs to be more or less taken care of. So first we have to actually perform this p minus integral, and how to do it we will see in a moment. Maybe you already know. And the second is, okay, I never actually told you what this gamma is. Oh, since I am lazy, I forgot. This gamma is for the definition of TMDs. Maybe I put a 1/2 at the beginning. I do not remember. This, if you want to compute the leading twist is bad naming, but let's say what is usually refers to is 2 TMDs. So okay, there are better naming conventions, but let's say 2 is 2 TMDs just for the sake of argument, as Neil presented. So you just have gamma plus over 2, or gamma plus gamma 5 over 2, or I sigma alpha plus gamma 5 over 2. So most of this is convention. You can use different bases, but the point is that these leading twist structures are the structures that involves only good components of the fields. And what are the good components? So if you have, in light from quantization, if you have your spinor fields, let's say C of Z, whatever, you can project out the good component by using a projector P that called just plus, which is gamma minus gamma plus over 2. And the bed component is just P minus, is projected out using P minus, which is gamma plus gamma minus over 2. So the meaning of these good and bad components is it has different level of meanings. One, which is the one which I am referring to now, is the bad component is a constraint component if you use light front quantization. So in principle, you can use light front coordinates, so using this plus minus as coordinates, but not using light front quantization. So you forget about quantizing on the light front. You just happen to use a different parameterization for space-time, and that's it. And you quantize on a surface which is equal time, which is what you usually quantization on equal time surfaces is what you usually see in standard classes. And that basically gives you nothing for good and bad components besides some argument on how they scale. Because the equation of motion, you can write them in light front coordinates, but the time is the usual time. So you get basically the usual equation of motion, which does not separate between components, even though you should have seen in classes like QED or quantum field theory, so basic courses, that you just get for quark fields, you get just 2 spinors with 4 components. Like you with positive helicity, you with negative helicities, but you have 4 components. So that is suspicious. Like so you have 4-dimensional objects, but with just 2 independent objects. And this is because, in principle, in reality, you have the bad component is there, and it is a constraint component, but you do not see it in instant for quantization. So the only form of quantization that single out this dependent component is light front quantization. Light front quantization, you quantize on the light front, so you impose your anti-commutation, in this case relations, at equal light front time, which is conventionally used as Z plus light front time. You could use Z minus, doesn't really matter, it's just conventions. And the bad component is dynamically constrained. So you get an equation, which is written on the document. I do not remember it by head, by the top of my head. So you get an equation in which the bad component of the field appears in a differential equation, so you can solve it given boundary conditions, in which the derivatives that act, the derivative that acts on the bad component is a spatial derivative. So you fix your light quantime, you solve this equation, this differential equation, which you can do, and you have a constraint component of the field. So it's called bad because it's not dynamic. You have to remove it one way or another because you do not have a time evolution equation for that component that is fully constrained given your diffusion. So in this case, you can convince yourself that if you take something that looks psi bar of y, one of these gammas, psi of z, this is equal. So let's say that p plus minus that acts on psi gives you psi plus minus. This gives you psi bar plus component gamma psi plus. Better? Yes. Okay. So you can convince yourself of this, but please remember how this actually, but this is kind of, this notation is kind of question mark. Usually what you should do is put in the plus under the bar, because you know this, but if you take the bar of this object, this is equal taking C plus dagger with the gamma 0, and I leave it to you to work out the culture. And you will see that, okay, if you use this definition, so C bar plus component is the bar of the projected plus component of psi. So you use this kind of way of computing it, you actually see that okay, this relation is true. And you can also play the game. Okay, you have in principle you have 16 direct matrices that you need, 16 objects more than direct matrices that you need to parameterize a general direct matrices. This is just naive. I mean, you have 4x4 matrices, so you have 16 basis elements. So you can just select 16 independent direct structures to parameterize your direct space. And it so happens that okay, 3 of these direct structures project out good and good components. Another 3 projects out bad and bad, and the remaining gives you 10 gives you the remaining good and bad components. So traditionally, if you work in collinear, and so not TMD physics, but if you work in collinear physics, plus components are twist 2, correspond to twist 2 PDFs. Plus minus components, so 1 good, 1 bad, correspond to twist 3 PDFs, and minus minus, so 2 bad components correspond to twist 4 PDFs. So this gives you also a nice way to compute, right? Can actually compute the collinear twist. So all of this to say that we, in some sense, need the fact that gamma projects out the good components. So it is one of these 3 matrices or 3 structures, because you have the integral over p minus, and you can just let us select just this piece right here, which is one of the 2 that appears, one of the many that appears, just for the sake of the argument. So you have gamma of p slash, which is nothing else than gamma of p plus gamma minus plus p minus gamma plus minus pt gamma t. So this is Euclidean. So now, if gamma is, let's take the first one, but it works exactly the same for the other 2. If gamma is gamma plus, you know that gamma plus is actually equal to 0, and you can prove it. And you just take gamma plus is nothing else than gamma 0 plus gamma 3 square root 2. You plug whatever this parameterization is into gamma plus, and you find that is 0. So the point is that the second term contains p minus gamma plus. So the plus minus mixture is typical of flat front coordinates. So the scalar product mix plus and minus. But if you select your gamma from gamma plus gamma 5, or I sigma alpha plus gamma 5, which incidentally this alpha is a transverse index, so it can be just it cannot be plus and minuses. This p minus gamma plus disappears, is 0, because of the direct structure. So all of this to say that in your numerator you do not have p minus, so you do not have absolutely to worry about p minuses in the numerator, which greatly simplifies the argument that follows. So now I really have to assume that I work with a gamma which lives in this 3-dimensional span. The span of 3. So what you get now is basically you just need to do a residual integration, right? So you are faced with, I hope you can see that is a complex integral, because you have this plus I epsilons. So you can actually choose how to deform this. I mean, not really, but you have to look at the integration over p minus into its complex plane. So this is the complex plane of p minus, and you have basically 3 poles, right? 2 of which is order 2 because it is the same pole, and you have another pole that comes from this operator. So the integral that you want to perform is along the real axis. This is just the integral over p minus. But you have poles in the complex plane, and you have to basically, to compute this, you introduce some path in the complex plane of p minus. So let me put a C just to tell you that this is the path, the path in the complex plane of p minus. And you will write this as, of course, the path should include the real axis. So you will have your integral over p minus plus an integral over something else. Yes, and that something hopefully is 0 in the limit of large something parameter. The path is closed, so you can actually apply the residual theorem. So you get 2 pi I, the sums over the poles of the residual of your function. So you basically can compute this integral over p minus using the residual theorem and just getting rid of whatever is this something. So excuse me, just one moment. Okay, sorry. So the problem is, where are the poles? So we have p squared minus m squared plus I epsilon, which is nothing else than 2p plus p minus m squared plus I epsilon. So this tells you that assuming small p plus greater than 0, that p minus is this. You ask when this is equal to 0, you get that p minus is, of course, this like minus pt squared. You get pt squared, in which incidentally pt squared is greater than 0. So this is Euclidean, really. Plus m squared over 2p plus, and this is just whatever, minus I epsilon over 2p plus. So, and this is really important. And then for the other piece, you get 2p plus minus small p plus, capital P minus minus small p minus mx squared minus pt minus small pt squared, again Euclidean, plus I epsilon equal to 0. And this gives you okay. So first of all, you assume that capital PT is actually 0. So the second piece is nothing else than small pt equal to 0, which includes the minus sign in front. You have that capital P minus, remember that the proton is, this is the momentum of the proton, and the proton is on shell. So you get just the mass of the proton over 2p plus. And then you assume that since you want to connect with TMD physics, in which small p plus is nothing else than some x times p plus. So if you take everything into consideration, this p plus minus small p plus is nothing else than capital P plus 1 minus x. So you get small p minus is mp squared over 2 capital P plus, which is capital P minus. Yes, the same sign. Then you have minus, because here you have a minus in front. So you change actually the sign. This is mx squared plus pt squared over 2p plus 1 minus x, where this 1 minus x comes from here. And then you have plus, again, because here you have a minus in front, so plus I epsilon over 2p plus times 1 minus x. So you see that, okay, here we assume that small p plus is greater than 0. So this is the important assumption. Small p plus is greater than 0, which means that x is greater than 0. And incidentally, x less than 1. And therefore, this, let's call this pole B and this pole A. The pole A is as negative imaginary part, so it leaves, and positive whatever else, so it leaves somewhere here. And okay, pole B could be positive or negative in the real part, depends on this mx, the pt square. So I do not really care, but just say that this whole combination is positive. It doesn't really matter, but positive imaginary part. So let's say that pole B lives here. And what you have in mind is that the diagram looks like this, right? And to connect with DMT physics, you want that this is cutted, which is exactly this integral over p minus. So you want to put your dipole on shell. You do not want, and okay, since we are basically saying that the second pole is the pole of the dipole propagator. This comes from the scalar propagator. So you want to put this propagator on shell. You want to cut this propagator, not the quark one. So you want to select this pole, not the first one. So what you can do is deform your integration, or actually this path is an integration over alpha circle that runs like this, with radius. Okay, this is terrible looking, but let's say that this is alpha circle, not alpha something else, and the radius is capital. It doesn't really matter. So you see that this function, this complex function goes like p minus, p minus, p minus for large p minuses, right? The numerator, I just said that does not contain anything. So you have the integral over a semicircle with radius that tends to infinity of 1 over the radius cube for large radiuses, radii. Therefore, you know that this is basically 1 over r squared for large r, which is, so if this is not clear, we can do the simple math. I hope that you can see. So the contribution from this something is actually tends to 0 for r that tends to infinity. So, okay, we don't care about it. And we are left with 2 pi I times the residual with plus sign, because we oriented the path in the standard way. So it's anti-clockwise. So we have nothing else to do than to actually plug everything in. So you get from the integrals over, did I forget? Okay, I forgot to carry this 1 over 2 4 pi, which comes from, sorry for that. It was just one contribution that I left behind. So you get I times g squared times 2 over 2 pi to the 4th. Then you have 2 pi, so 1 I and 1 2 pi comes from the residual theorem. Then you get, what did I say, the minus there? I do not really know, but like an extra minus is, sorry, I do not see it right now. 1 minus x, 1 over 2p plus times pt squared plus L squared, everything squared, where L squared is x m x squared plus 1 minus x m squared minus x 1 minus x and p squared. And then you have your u bar of p slash plus m times gamma times p slash plus m. Sorry, this is p slash plus m u p. I do not know what dependent does. So this is just algebra from the denominators. So what you have to do is, okay, you identify the pole, which is the relevant pole is this. So you just have to basically plug this definition of this equality for P minus into your first two propagators. This is removed by the residual. So you just have to compute these two denominators at that values of P minuses. You can do it by hand, by mathematical, whatever you want to do. It's just, there is really nothing there, just plain computation. You just plug it into that. And oh no, sorry. Okay, this minus is this is bullshit. I just in my notes I just removed the. Okay, that minus was this I squared. So you get you can simplify 1 to pi. You can this becomes minus this 1 minus x comes in the denominator actually. So the not important. So now basically, okay, you have some kind of prefactor, which looks kind of ugly, but who cares? And then you have your direct structure. So basically what you, and besides saying that gamma is gamma plus half, gamma plus gamma 5 half, and pi sigma alpha plus gamma 5 half, we really did nothing to specify this direct structure. So you can more or less say, okay, who cares? But now you can, what the game that you can play, I would advise against doing by hand if you have mathematical or whatever other software to do manipulations, because it's just boring and not very instructive. But what you can do is actually compute this direct structure for all of three matrices. And you end up with a list of 6 TMDs, depending on the polarization, not 8, because we do not get the Sievers and Ball-Mulder's TMDs, right? Because we do not have the Ricci. So that is, first of all, a good check that you do not get them. So it's really linked to the gauging effect. And second, it's just, okay, you have a list of stuff. But now I was really sneaky, and I never told you if the proton is with some kind of helicity lambda, if the proton is with some kind of spin S, just because I was lazy and didn't want to carry all the way. What you can do usually in TMD physics is to define your TMD correlator as diagonal in this momentum and spin representation. However, we know much better how to treat helicities compared to spins in kind of how we write the operators. So how do we do that? How do we connect the two views of your TMD correlator? Is that whatever this, let me call this phi S, which is your correlator. I mean, phi usually is standard name, you other dependencies, whatever, I don't care. Right now, I just care about the representation of the initial and final state in terms of spin / helicity. So just forget about everything else, doesn't matter. So phi of S, you can actually write it as 1 plus lambda over 2 phi plus plus, where I write phi lambda prime lambda as the correlator. So in helicity representation, the correlator is not diagonal, of course. It is diagonal in the momentum, but not diagonal in the helicity, of course. But in the spin representation, it is diagonal in the spin. It's a different view of the same thing. So here you have 1 plus lambda over 2 plus 1 minus lambda over 2 p minus minus plus s left over 2. Well, now I will tell you what this s left and s right are. Plus minus plus s right over 2 p minus 2. So you can just play the game of computing it with this phi s correlator. You plug these definitions into your I mean, you compute phi plus plus as u of lambda equal plus 1/2 p. So I think that I use up and down arrows, just whatever. And U bar of plus, minus, up arrow, down arrow, whatever. You have your combinations. You plug this, and you end up with a list of results. They are not really informative. I mean, they just look in the way they should look. And S is the proton spin 4 vector is defined as this lambda p plus m minus lambda m over 2p plus, and then SL is S1 plus I S2. Sorry, R is with the plus, S left is S1 minus. This is right and left are nothing else than instead of linear polarizations in the transverse plane, you use circular polarizations in the transverse plane. So right-handed and left-handed polarizations. This is standard. I mean, there's really nothing there. It's just convention. And this lambda is parameter, of course. So this lambda is not linked with this plus and minuses. This is the lambda that appears in the definition of your TMDs. For example, if you use gamma plus, whatever fields here, gamma plus gamma 5, whatever fields here, PS, this is parameterized as lambda G1 x kt, or small pt in my convention, plus whatever other distributions. So you can take whatever table which gives you the standard parameterization of the TMD correlator, and if you plug gamma plus gamma 5, you will see this lambda in front, which is the polarization of the proton. And if you do the same with the I sigma alpha plus gamma 5, gives you the transverse polarization. So it's SR, SL, or S1S. So there is really nothing. I thought that it would have taken longer. Okay. There's nothing much else to be said about the dike work at this level. Just a couple of remarks. First of all, we use scalar dike works. You can just do the same exercises with a vector 1 particle, which is remarkably similar to quark target model, okay, in which you see the correlator. These are just quark fields, and you radiate a gluon along your cut. So this is known as quark target model. It's really nothing there. I mean, it's just standard perturbative calculations in QCD, which you can do, just fun with it and learn to do it. And okay, you can, and this goes into the line of the question that I asked, you can actually enhance the theory a little bit. And for the dike work, it was done to include the interaction with the gluon to actually compute the Sievers and the Bernoulli functions. And for that, you need to just be a little bit more aware of what the hell you're doing with your Lagrange. So I just wrote something that was kind of terribly concise, right? This was the Lagrangian. Of course, okay, the only comment that I made is that, okay, here you saturated your structure, good. But now, okay, if your proton is colorless and your spin 1/2 particle that you could quark is with color, so you should get the scalar dipole with color. But there is really nothing that you can do there. If you want the capital psi to be color neutral, then phi must have color. You can't do anything about it. And you can okay, you can have color, but you forget about the interaction with the gluons. So it's okay, you can do it. Otherwise, you have to write what is the scalar, basically scalar gauge theory. So you write your gauge theory, which is color gauge theory as CO3, but with scalar particles instead of spin 1/2 particles. So the gluons remain the gluons, but you have scalars instead of spin one. It's a little bit more ugly looking. It's not really, I mean, it is not pretty, but you can do it. And there is also scalar QED if you don't want to use QCD. You can do it in principle, and then once you have the interaction between the diquark and gluon, what you can do is computing the first approximation of the Sievers function, which looks like this. This double line here indicates, sorry that I use the same kind of notation for the proton. This is Wilson line. And you can actually compute this interaction, right? And this is the proton. So you can compute this. Of course, this is perturbative calculation, so it's really does not really encapsulate the full picture, but still you get something out of it. One can say, okay, let's forget about this Wilson line by using Lagrange gates. They already told you that this is a really bad idea to do it in TMD physics, because you then get this. First of all, in Lagrange gauge, the propagator for the gluon is much uglier compared to Feynman propagators in covariant gauges. So the Feynman propagators in Lagrange gauge is actually a mess compared to standard covariant gauges. So it's already more complicated. And then you're still left with the transverse link at infinity, which you cannot put to zero. I mean, you can put to zero in CDs, but then you have a non-zero in Drellian and vice versa. And that's kind of depends on the gauge that you're choosing to use, but it's always Lagrange gauge with different boundary conditions, so it's really different physics. And in principle, also it affects the definition of initial and final protons, because you put different boundary conditions at plus infinity and minus infinity. So overall, to say not wonderful idea using Lagrange gauges to do this kind of calculations, because it brings you complications more than clearness. And also, I mean, this is shameless plugin, but we actually show that, okay, in this diquark model, you can derive relations between different distributions, different types of distributions, so TMDs and impact parameter distributions, which is absolutely nonsense in the full theory, because you cannot have relations between them. So that there were some features of this diquark model that actually allowed it to be the case. And one can show that, okay, that's kind of relate on how actually this diquark parameterize the Riemann. That is, if you use a point like scalar particle, you get those relations just because you don't, your theory is not rich enough to accommodate for different structures. So this is just, okay, diquark theory as it is not rich enough. But you can actually, okay, just play around with it. Not just because you get results out of it, but because we do not have many examples of theories, right? You learn QED, QCD, maybe you do something about weak theories, but never in great details. And I don't think, because they brings a lot of algebra and not really much insights usually. So here it's kind of a stupid example of a theory that you can actually, I mean, compute loops. One of the questions was, can you draw the loops for this theory? So one loop, if you want the quark that exit, the proton, let's write this as proton that enters, and the diquark that exit. Okay, so this is your question mark. So this is just tree level plus, and then you have whatever. Enter proton. So this is scalar, this is proton, this is quark. So it is kind of strange looking, because we do not, I don't think we see theories like this very often, with three particles interaction at a single point. But you can compute this loop, basically. And if you replace the proton with the quark, you can see very similar, you can see a lot of similarities with QCD, right, more or less. Even if not completely. So you can do it. you can try to compute this. Okay, this I do not know. Okay, yes, this arrow was, of course, this arrow is wrong. This arrow is in the other direction. That's the flow. You can actually compute this. You can play around with it. I mean, but you learn. It is a test to see, okay, I really understood how the beta function emerges in QCD. So how it actually works. Because if you do QCD, you get just, okay, the results, you compare it, you do it with half of the brain off because you already know how to do it, because they thought it, you saw it before you could actually do it. So this is a nice, I think, way of exercise and familiarize yourself with loop and all kind of stuff. So now it's kind of excellent time for a break. So I will stop here for, like, say 10 minutes. We can resume at 11:25 if it is okay for everybody. If there are questions, I will take them. Otherwise, 10 minutes break.
Very good, Simone. Well, no questions apparently.
They're all dead.
No. Okay, then we'll think about possible questions during the break, maybe.
Yeah. So I will
Okay.
be back in 5 minutes. Just
As you want, as you want. Okay, very good.
if the level is too simple, let me know. If the level is too difficult, let me know. If you have questions, let me know. So my mail is somewhere in the document. You can actually write an email, just say, hey, I didn't understand this, or can you cover that, whatever. And so if you do it before tomorrow morning, I can look into that. If you do live tomorrow morning, I will give what I thought in the moment. But don't be shy. So, okay, I think I'm much closer to your age than to any of the professors. So this is for your benefit. It should be for your benefit. I mean, if you get nothing out of the school, it's really bad. It's really sad. So please, whatever it could be. If anyone cannot answer, I think that we can start again. I mean, I see that they're basically the same number as before. So now I will take some kind of less computational heavy topics, just kind of general purposes and kind of nice things to know about the different distributions. So, and by the way, I will consult with Professor Pasquini for what to do tomorrow, because I didn't thought it was that I would have finished the topics today, and we will see. So first of all, is on the menu is the Platonic interpretation. Of GPDs. So I think most of you can actually guess it, and just do it by yourself. But it is kind of nice to look at it a little bit more kind of formally. So as I quickly said before, but now it's kind of put all the details. Let's say that we have the good component of the quark field evaluated at z plus equal to 0, z minus, and then I will use the light convectors just to give it a proper meaning. So z minus n means z minus in the direction of n, which identifies the minus direction, and zt. And this is the Lagrange invariant measure that written explicitly is k plus the kt, which is two-dimensional, over 2k plus, which is the is the on-shell, the part that comes from the on-shellness condition, 2 pi cube, then theta of k plus. So these are the standard ingredients of light cone of Lagrange invariant measure. If you write it on the light cone, because you use k minus to impose the on-shellness conditions, you get, and since light cone coordinates mix plus and minuses in the scalar product, you get 1 over 2k plus instead of the what usually should be the energy, so the square root of the mass plus whatever. So just a different way of seeing it, basically nothing there. And then you have the sum, and also here I was kind of using the common knowledge of the field, but this is the light frontalicity. So it's lambda is up and down, and light frontalicity is kind of a slightly different concept compared to standard helicity. So please, there is the standard reference of Soper, I think it was, that it is cited. This is one of the 5, 6, 7 whatever papers that I cited. Please go look into that. It's not complicated, just a little bit of algebra, and you understand it. You should be clear. The paper is well written and kind of very, very clear, I think. So it is not really important. It is up and down for us, labels, but it is not the standard helicity. So please keep that in mind. And then you have the annihilation operator of the quark. So that depends on k plus, kt, and the helicity lambda, u component, u plus component, which means good component of the quark spinor, k plus lambda. Why I do not put k perp? Because you can check it that if you take the plus component of the spinors, the transverse momentum drops. And then you have E minus I kz, and remember please that is z plus equal to 0, so just I do not write it, plus the anti-quark k plus k lambda t plus of k plus lambda d I kz. I remember you that is z plus equal to 0, and okay, as we saw before, I mean, z plus equal to 0 means nothing else than integrating out the off-shellness of the particle. So this is the quark field on shell, and this is what the Lagrange invariant measure is telling us: put on shell. So I think that one of the structure that I asked you to compute the Platonic interpretation was integral over z minus over 2 pi e minus I x p plus z minus, where since we are working at the level of operators, this capital P plus is just a positive number, just plug it, whatever, just to have the definition in terms of x. But it doesn't really matter at the level of the operator. Once you sandwich it between states, of course, P plus becomes the P plus momentum of the state. And then should have been this plus, remember this from before. Or, and here just to annoy you, really, I use a different convention. Not, you see that here there is a minus, and here there is a z over 2 instead of a 0. So you should be kind of familiarize yourself with different notations. First of all, because different works use different conventions, and second, because it gives you kind of better understanding. I think if you work just with one convention, usually you don't think much about it. You just use it and forget about what it really means. So it's useful to switch sometimes, just to keep okay. Did you saw my did you see my screen? I mean, have you been able to see my screen up to now? because it gives me it gave me a strange kind of pop-up. I think so.
Yes.
Yes, yes.
Oh, okay, perfect. Otherwise, you were
Yes.
dead. Okay, thank you, thank you. So okay, so you have gamma plus over 2, which is this is what previously I called gamma, more or less, and then 1 plus gamma 5 over 2. So this is kind of a combination between gamma equal to gamma plus over 2 and gamma equal to gamma plus gamma 5 over 2. Right? It's a combination of the two. Why? Why not? Just, I mean, since we have one convention, it doesn't mean that we have to use it without thinking. You can use different conventions with different gamma matrices. In this case, there is also some slight meaning behind it, even if it is not conventionally used, but you can see that it's basically 1/2 the sum of gamma equal gamma plus gamma equal 1 plus gamma 5. Right? There is really nothing to it. You just take 1/2 the sum, and the corresponding structure is 1/2 the difference, and you construct different distributions out of this, or you can see the distribution that you construct out of this as combination of the standard distributions, whatever. And then you have C plus of minus Z. So what you need to actually see the Platonic interpretation. So the Platonic interpretation is nothing else than, and here I didn't put the gauge link. Forget about the gauge link for now. This is this is collinear operator, so we can just plug E plus equal to 0 and forget about the gauge link, and without really worry about anything else. Choose A plus equal to 0 to get rid of the gauge. So to see the Platonic interpretation in this gauge, you would like to see, I mean, here you see that enters, a quark field enters and a quark field exit, and you would like to see, okay, which momentum does these two states have with respect to this capital P plus and with respect to each other, and which kind of helicity. And I mean, here I really draw this as quarks, but could be this something like a pair that enters and nothing that exit, but quark anti-quark, or could they be anti-quarks? This kind of reverse, right? So these are the questions. Basically, you ask a bunch of, okay, what is the structure of these things that enters this X non-local annihilation of your operators. So what you need actually is, first of all, the parameterization that I wrote. And since you're going to saturate the near structure, you basically need a beautiful table of possible combinations. So the point is, and I told you here, I put the plus because I know that gamma plus and gamma plus gamma 5 projects out the good components of the field. One good check is, do not project out the good components, just plug your generic field here. I mean, here it's already written with plus components, but okay. You can forget about the plus here, plug the generic spinos, and really check that using plus spinos or generic spinos gives you exactly the same result, which it has to be because this structure projects out to the components, but you can actually check it, which is nice. I would advise against doing this computation by hand, just because it is long and boring. But you can if you want. So you need a table in which I think you can read the meaning of the table quite easily. So U up, U down of K, V up of K, V down of K, right? And then and this is the Dirac structures associated with psi of minus Z over 2. And in the column, of course, there is the one associated with psi bar. So it is U bar half of Q U bar down Q, V bar up Q, V bar down Q, right? Yes. Perfect. So first of all, you start to see that this is 0, this is 0, this is 0, this is 0, 0, 0, 0, 0, 0, 0. So you've got a bunch of zeros, like in an X shape, which is kind of, you breathe, you say, okay, it's fine. I do not have to do so many computations. And you can actually kind of check it by either the meaning of this 1 plus gamma 5, which actually projects some specific felicities for the quark. So you can just think about quark, so quark spinors U bar U, and you realize that 1 plus gamma 5 projects up and cannot and annihilates anything that is down for the quark. So you can actually see that this upper left quadrant should have 0, 0, 0 whenever you have a down arrow quark, and the same basically happens for the down right quadrant, right? So you can use reasoning like this, and then of course when you switch to relate quarks and anti-quarks, this changes. I mean, you can see in the anti-quark 1 plus gamma 5 actually projects the down, so not the up. So just the magic, and also the structures are quite simple. It's always 2 square root of k plus q plus with incidentally minus sign somewhere. So if you look at the table, is beautifully symmetric, so it's kind of very okay. And I didn't, maybe I've written, maybe not, the parameterization for the electron spinors that I put, which by the way is really standard. You use the Dirac representation of the Dirac matrices, or the standard one, not the chiral, not anything strange. So just the ones that you need, but you can work out the others. This is the identity. Oh, by the way, sometimes I write 5 up or 5 down is the same stuff. So this is standard parameterization, where sigma 3 is the Pauli matrices that looks like. No, this is not sigma 3. This is nothing. So that should be quite standard. But the table is simple to compute. It's kind of automatic. So the operator that we needed was the integral over z minus 2 pi minus x p plus z minus. Then we have the the 2 Fourier transforms for the psi bar and psi fields. So just to keep the same nomenclature that I used, is the q plus the qt over 2q plus 2 pi q, it of q plus, the integral over the k plus, the kt over 2k plus 2 pi q, it of k plus. Yes. Then you have and now I'm just I'm doing nothing else that selecting this for this. Sorry, I was using my fingers. Of course, you cannot see them. These 4 cases, right? So I'm using these 4 cases, and everything else is 0, to plug them into my parameterization, my expressions for the spinors fields, and just compute them. There is nothing else. The Dirac structure of this is worked out in the table, and you just associate with the correct operator and with the correct sign for the expansion, which incidentally I got one the first time. So here you have E I Q Z alf, E I K Z alf. These are all for products, but with the additional condition. I mean, for products, not really. I mean, the operator is at Z plus equal to 0 and ZT equal to 0. So, okay, these are intended as for products, but then we just plug Z plus and Z perfect ZT equal to 0. So we just get the relevant component. So here, this is B dagger of Q up, B up of K. And you can see that, okay, since the second one is evaluated at minus Z over 2, the two exponentials have the same sign. So this should be okay. Then you have the mixture between quark and anti-quark. So this is E I Q Z alf, E minus I K Z alf, in which you have B dagger up of Q and the dagger down of K. And then you have the other part of the table, in which you have E minus Q Z over 2, E minus I K Z over 2, in which you have D, what is it, down Q, D dagger down of K, in which you see that you use, I mean, the antiquarks are given in the opposite order compared to the quark operators, and this is minus I Q Z alf, E K Z alf, D down Q, B up. Okay, and everything is multiplied by, let me put it here, K plus Q plus, right? Which was the factor that comes from the table, and you see this minus signs, which comes from the table. So you have not really different as from before. You what is a Fourier transform, and you have your exponentials, and here you get basically the Fourier transform, something that looks like xp plus minus, let's say, some combination of k plus and q plus. This f is, it is just shorthand. I do not really care. It is plus minus. I will write down the complete expression. And this, you know that from distribution theory, you just get this, right? So I will take out the p plus and just write it. And this is kind of nice because this 1 over p plus cancels, more or less in the sense that it cancels the dimensions of this square root of k plus q plus. Just nice thing that happens. So this gives me the integrals over the Lorentz invariant measure of k and q, which here I've written explicitly just for your convenience, but kind of they are the Lorentz invariant measures. So you can use the shorthand notation. This is k plus q plus everything over p plus, and then you have your operators. This is b dagger up q, b up of k times the delta of x minus k plus plus q plus over 2p plus, where where this 1/2 comes from these 1/2s that are in the positions. And then you have the list of others. I will not write all of them. Just one of the, let me invert one of them. Just, I think that you have the result, and if you do not have it, it's just really simple algebra. Okay, then x minus q plus minus q plus q plus, and so on and so on. So you just get a bunch of different structures, and one thing that you can notice is that let me write also this: b down of q, b direct down of k delta of x plus q plus k plus over 2p plus. Just I wrote this just because you can appreciate that these two combinations are the same and they are positive. Correct? I mean, the Lorentz invariant measure tells you that k plus and q plus positive, p plus, capital P plus is positive. So in the first line, you get x equal to something positive. In the last line, you get x, and here you have, of course, the equivalent of this part. In this line, you get x equal to something, to minus something positive. So x is negative in the last line. And this tells you basically that you can relate the quark distributions and the anti-quark distributions by simply reversing the sign of x. And then you get plus signs or minus signs in front of distributions, depending on the Dirac structure that you're using. So this, you actually see in action that the anti-quark distributions can be obtained from negative. From the anti-quark distributions are linked to the quark distributions by taking the negative argument. And this is powerful, and this boils down from the fact that you do not have a separation. I mean, you do not have a separation between quarks and anti-quarks at the level of the position space operator. So when you compute stuff that are written in terms of the position space operator, you for free gains this kind of relation between positive and negative momenta that raise quark and anti-quark distributions. So if you have questions on this, although I think it should be quite intuitive, please ask. And okay, this is, I will, I will start with no, I think that if it is okay for everybody, I will stop here so you can have an early lunch and recover. And tomorrow I will finish the last of the arguments that I'm supposed to tell you about, which is the connection between impact parameter distributions and GPDs. So I will do it at the level of correlator. So just, I mean, I think that you saw that the Fourier transform actually. So you know that the final point, it's kind of few lines of manipulations, not really much. And then okay, if you have something that you want to see, really, either discuss amongst yourself and bring it up, or I will either otherwise I will discuss with Barbara and see what we could do. So if there are questions, I will take them. Otherwise, everybody I think can have lunch.
Can I ask a question?
Yeah, sure.
Okay, so in your document in the exercise 7, you you want us to calculate the the time reversal operator, right?
Yes. Yes.
Yes. So
I mean, I said yes. Just give me a second that I bring up.
Oh, okay, okay.
So I can actually maybe I can. 4, 7. Okay, yeah.
Yeah, so actually I have already done this kind of calculation, but I made some, how to say, I made some problem. The problem is that when you go back to, how to say, when you go back to that 2.5, you will say that under time reversal, actually, for example, k plus will go to k minus. And then how do we calculate this kind of thing while we are doing time reversal?
Oh yes, yes. Then okay, that's common. Sorry, I was sloppy because usually when you say that you use time reversal, usually you pair it with parity transformations, right? I cannot give you a reference right now, but I will share something. You usually pair. I mean, that's the point that you bring up. You with time reversal, you mix. I mean, you go from plus to minus and minus to plus, and to restore it, you use parity, which basically do the same. Yes, that's it. Basically, you just get whatever is x and xi goes to the corresponding into the minus version of the momenta with time reversal, and when you use parity, you bring it back to the plus mode. So I will share it. It's sorry, I was sloppy, and okay, that's common practice.
So you mean that it's for example, this C here is, how to say, for example, if we go back to the instance form, how to say, the ordinary QFT, we will understand that actually this C here is just how to say, is just a matrix, right?
Yes.
Yes, and so you mean that actually here in the light from, how to say, in the light from calculation, this C here is actually not just how to say, matrix. It's matrix
no. I mean, here you don't. Here you use light front coordinates, which you can do in standard quantization. There is nothing there. You just you do not need to use light front quantization here. So C is the charge conjugation matrix, which I think from the top of my head is something like I gamma 2 gamma 0, something like that. And if you want to use light front coordinates in all your calculations, you just replace gamma 0 with gamma plus minus gamma minus over square root of 2, something like that. But you are not forced to. I mean, think about as here we are using light front coordinates when it is useful. So for the momenta and whatnot, we use the plus minus coordinates and the transverse. And for everything else, we can still use our standard coordinates because they are the same. They are just linear combinations of one another. And forget about for this part, you can completely forget about the light front quantization. So you really do not need it. It's just manipulations at the level of fields like this. And in fact, I see that, okay, I put the bar in standard Lagrange parameterization. So it's 0, 1, 2, 3. You can use plus minus, and you see that you exchange plus and minuses. That's up to you. But okay, I reiterate, for this part, you do not need to use light front quantization. So please, if that confuses you a little bit, or just you're not really used to, you can think of this part as standard quantization.
Okay, so you mean that while we are doing exercise 7, basically we can forget 2.5 and 2.7, right? 2.5 and 2.6, something like this, right?
Yeah. I mean, you do not need, for exercise 7, you absolutely do not need to go to the momentum space representation for your spinors. It's really just manipulations at the level of the matrix element that defines the GPDs. So where is it? Where did I put it? Well, let's take this, but just because I do not know where to look, I forgot. You can just manipulate. This is not a good example. You can just manipulate this basically 3.3, right? Or if you focus on H, just say that it is 3.4, which you have gamma plus, And here I see that I
Okay.
use the opposite convention. So you just manipulate this. Do not do any extra transformations, any extra go to momentum space. This complicates matters. Just I mean, there is no need. So you can just manipulate this as it is with the rule that I give you.
Okay, so so maybe I have to formulate my question like this. So is there any way that we can deduce 3.8, how to say, from using 2.5 and 2.6, something like this? Because if we are using the, how to say, ordinary quantization, then basically Paskin's book just textbooks, how to say, procedure. But while we are using 2.5 and 2.7, then something gets.
I mean, I'm not completely sure I understand it. Your question, so just let me. So you're asking if, okay, you should see. So if, let's say that we have this operator, psi of 0, psi of z, whatever the gauge link in between, the Fourier transform, and the matrix element, right? This is P prime, this is P, right? So this is the sketch of the operator. And you're just, okay, let's say that 2.5 is something that tells you that this C of Z that you write as the Lagrange invariant measure, then you have the creator as just wrote, and then you have your spinor U, whatever, okay. And you want to use the explicit parameterization of this to see the relation. You can do it. I mean that once you say that the time reversal operator acts on psi of Z T, this is an F, sorry, this is not a T. So I said T minus 1. This acts as whatever prefactor, the charge conjugation matrix of C of minus Z bar, right? And then you can just, okay, this is, you switch plus and minuses, so be careful with that, but you can just, this is quark spinor field at position whatever minus Z bar. You just, and here you have minus I ZK. You just plug this minus Z bar here instead of Z, and then you can play the same game. I mean, you can. This is an integral, so you can change variable, right? You're allowed to change variable under the integration sign, with the caveat that goes with it. So you have to change variable in the kind of correct way, so you play it, and you can reduce this exponential to, I do not remember from the top of my head if it is plus or minus, but I would guess it is a plus, but don't take my word for it. This is Z bar K bar, and then you have your B of, since you changed the integration variable, you get B of K bar, and then your spinor of K bar. Right?
Yeah.
Okay, and then you just let's say roll the argument. You just the only point is that, okay, you have to change variables, do it in a consistent way to just get this scalar product in the exponent, and then it should go basically automatically, just to carry it to the end, I think.
So how can we, how to say, is there a way that we can prove this this T psi T minus equal to something else?
I mean, so your question is this exactly 3.8?
Yeah. How do we prove this? For example, how do we deduce this?
This is not deducible. This is the action. I mean, when you probably there is something very general, which I really am not aware about, which gives you this T psi T minus 1 is the action on the Hilbert space, and you want to parameterize it. I mean, psi is both an operator in the Hilbert space and kind of explicitly written as a Dirac spinor. So the action on the Dirac space is translated into an action on the Dirac spinor. and probably I will look into that. I honestly, I never kind of, or if I did, I do not remember. I did kind of actually deriving this exact formula in light form quantization, but I think it can be done. I will look into that and give you an answer tomorrow.
Okay, thank you very much. Thank you.
You're welcome.
Excellent, Simone. Very useful. Huh?
Thank you.
So, if there are no other questions, we will see Simone again tomorrow morning. Think to other questions as you have already done, which is very good. And okay, we have lectures at 2 with Laura Toulouse, first of all, and then Barbara Pasquini.